Buongiorno.
Good morning, my name is Chiara, I'm one of the volunteers of Bergamo Scienza. Before starting, I would like to tell you that it is possible to connect to the site bergamoscienza.it and have a look at the program live. It is possible to follow the streaming in direct live YouTube on the site of Bergamo Scienza and on the Facebook page. From the channels, you will be able to send in questions to speakers or invite followers and friends to follow the streaming live. The web questions will be received by the volunteers, and we shall be asking one during the debate. The conferences from the 22nd edition of Bergamo Scienza are accessible also to people with motor and sensorial disabilities, trying to guarantee places which do not have architectural barriers. And all conferences are video recorded, some of which are also broadcast streaming. The conferences with foreign guests have simultaneous translations. Recording will be published on our official channels at the end of the festival. These services have been made available thanks to Fondazione della Comunità Bergamasca and Fondazione Banca Popolare di Bergamo, which together with Bergamo Scienza are very much committed in promoting inclusivity and accessibility. For simultaneous translation, it is possible to download the QR code that you see behind me, or you can ask to the volunteers in the room. The QR code will address you directly to the Converso web app. You will be able to select the translation language from the menu. To listen to the translation, you need to have headsets. Please use yours, or you can ask volunteers for some. Welcome to today's event entitled "Are We to Expect a World Without Antibiotics?" And we have Stewart Call from the Pasteur Institute in Paris and the University of Oxford, whilst the conference will be chaired by Luigi Ripamonti from the Corriere della Sera daily. Please mute your electronic devices and take part numerous to our activities. Thank you. Thank you very much and welcome, and thank you very much for having come so numerous to this conference. And it's a very good idea to be numerous because the topic is so interesting and so important. Are we to expect a world without antibiotics? ? Well, this is a bit of a rhetoric question, but we will hear about this from Professor Cole. Let me just mention the problem to start off with. Antibiotic resistance, so the capability of bacteria to become resistant to the action of antibiotics, is a problem that has existed since when antibiotics are being created, so from penicillin practically, because bacteria learn how to defend themselves, as Professor Cole will be explaining. But this is a problem that we do not really perceive because it seems that antibiotics are sort of taken for granted in a way. But this is not exactly the case, because just think that in Italy alone, every year, 11,000 people a year die because of problems associated to antibiotic resistance. 500,000 hospitalization days for this. We calculate 200 hospitalizations a day connected to this problem, not to mention the world figures that maybe Professor Cole will give you. I read on the Lancet that we are expecting 39 million deaths in 25 years. Now, the problem is so huge that even at the end of September at the UN, there has been a conference, an important conference to try and understand what could be the strategies that we could adopt so as to try and solve this problem. A problem that we perceive today as something that doesn't really have an impact on us. But let me tell you a story about my family. My uncle, who was born 100 years ago precisely, he played football when he was young. And a friend of his fell down as he was playing football, he had an infection and he died from it. He was only 15 years old. For us, it seems unthinkable. But without antibiotics, this is what we are to expect. we shouldn't only think about the fact that certain surgical operations will not be, we will not be able to do them, or transplants even. It's an enormous problem. We are in Bergamo. I am in Milan. We remember what COVID has meant. It has hit very harshly here in Milan. And somebody has defined resistance as a slow motion pandemic. So a slow motion, silent pandemic. It's like COVID, but we're not really seeing it. We don't realize it. Well, I leave the floor to Professor Koch, who will really be explaining to us how things are. Thank you, Professor.
Okay. Hello, everyone. Lovely to see you. I'm absolutely delighted to be here in Italy once again, and especially in Bergamo, which is such a beautiful city. And I would like to applaud the organizers of this science festival, because science is truly important. Science is transformational, and occasions like this give people like me, practicing scientists, the opportunity to share ideas and information with the general public. Today, I have chosen to talk about antimicrobial resistance, AMR. And this has been identified as one of the major threats to global public health. And if unchecked, it could negatively impact our way of life. And as Luigi has just said, AMR is a hidden pandemic. So I'm going to start with an introduction to antibiotics, and then I'll give you a simple science course lesson. Then I'll explain how AMR arrived. I will tell you something about the scale of the pandemic, of the problem. We'll get into demographics. And then I'll talk about the difficulties of producing new antimicrobials. And as you'll see, they're not necessarily scientific difficulties, but economic ones. I will give you an example of a rare success story in the field of AMR, and then I will end by showing how you can help. So, as Luigi said, about 10 days ago now, in New York at the 79th General Assembly of the United Nations, there was a special session on, on AMR. Where the world leaders and their representatives discussed what could be done, and they produced an executive statement at the end of the conference, which you can see on the right-hand side here. World leaders commit on decisive action on antimicrobial resistance. And if you read the bottom line, this means including a target to reduce human deaths from antimicrobial resistance by 10% by 2030. So I think this is to be welcomed, but it is a rather modest goal, but I think it is at least attainable. So that means we hope to reduce, to save somewhere in the region of 100,000 to 500,000 lives by 2030, thanks to the new measures that the world leaders wish to introduce. So let me now explain to you what antibiotics are. So the word antibiotic comes from the Greek bios. So an antibiotic is an agent against life. And as you've heard from Luigi, and as you well know, antibiotics are the foundation of modern medicine. It's almost 100 years now since the first antibiotic was discovered, penicillin. Antibiotics were first used to treat infections, but have subsequently found much broader application in preventing infections in medical interventions, such as surgery. Antibiotics protect cancer therapy, and they also make organ transplants possible. It was the success of the discovery of antibiotics, the first, should we say, rational medicine to be used against infectious diseases, which really launched the pharmaceutical industry. And it's, as you'll see later on, it's ironic to see that nowadays they're not so interested in this topic. I would like to show you a brief history of antibiotic development, and it's very focused on penicillin, the first one that was discovered. So this was, you're probably all well aware of the discovery by Alexander Fleming of a mold growing on a petri dish seeded with bacteria. And what he noticed was that around the mold, the bacteria were killed. And this was because the penicillium fungus was secreting the antibiotic. So scientists then tried to identify and isolate this antibiotic, and it was done first in Oxford. And at the beginning of the Second World War, the production of penicillin was scaled up to industrial levels, and it then became widely used in the ensuing years. And in this period, several other antibiotics and antibiotic classes were also discovered. Now, it's nearly 40 years, or more than 40 years, since the last class of new antibiotics were discovered. And in the early 2000s, we suddenly realized that antibiotic resistance was now threatening the existing treatments for infections and undermining the foundation of modern medicine. So action needed to be taken. But before I tell you about the action, I'll continue my simple science lesson and explain what antimicrobial resistance is. So AMR occurs when the bacteria that are responsible for infections such as pneumonia, sepsis, or tuberculosis become resistant to the treatment by antibiotics or by other antimicrobial medicines, things like antiseptics, for instance. Now, the bacteria can resist drugs in several ways. Some bacteria are naturally resistant because their cell envelope prevents the antibiotic from getting in. Others can change their structure in the presence of the antibiotic to prevent it entering. And then a major mechanism of resistance is actually the destruction of the antibiotic by an enzyme, a catalytic protein. And I'll give you an example of that. One of the scariest things about the AMR pandemic is the fact that the genes which code for these resistance mechanisms can be transferred horizontally. So the bacteria, they swap their genes, and this means that a previously susceptible bacterium can acquire a resistance gene from one of its neighbors and become resistant itself. This slide presents you with the timeline for the emergence of antibiotic resistance. And I'm going to start by reading out this citation from Sir Alexander Fleming, the discoverer of penicillin. Fleming said, "There may be a danger, though, in underdosage. It is not difficult to make microbes resistant to penicillin in the laboratory by exposing them to concentrations not sufficient to kill them, and the same thing has occasionally happened in the body." And you'll notice that within a short period of time after the first clinical use of an antibiotic, be it penicillin, tetracycline, macrolides, or quinolones, that antibiotic resistance is first reported. So 4 years after the introduction of penicillin, 5 years after the introduction of tetracycline, less than 1 year after the introduction of macrolides, and 3 years in the case of penicillins, of quinolones. There are ways of preventing this resistance from emerging, for instance, by using a combination of antibiotics or by using antibiotics in a better way. So let's continue the science lesson and see how penicillin, which belongs to the beta-lactam family of antibiotics, how it works. So you all know that bacteria are protected by what's called the cell wall. And the main component in the cell wall is a macromolecule, a large molecule called peptidoglycan. And peptidoglycan is only found in bacteria. And this is why beta-lactam antibiotics are so good at killing bacteria and nothing else. This part of the slide shows you a schematic of a bacterial cell. Peptidoglycan starts in the cytoplasm, the synthesis starts here, and then it continues outside the membrane in what's known as the periplasm. And there are two broad types of bacteria. There are gram-positive bacteria. These have a simple inner membrane made of phospholipids, and then a large layer, a very thick layer of peptidoglycan outside them. There's another class known as gram-negative bacteria. These have a thinner layer of peptidoglycan because they have an additional protective sheath around them, another layer of phospholipids known as the outer membrane. In the outer membrane, there are proteins known as porins which act as channels. Antibiotics diffuse through these channels and then reach their site of action. So one way of becoming resistant is to change the channel so that it no longer allows the antibiotic to enter. Broadly speaking, it is more difficult to treat an infection by a gram-negative bacterium because it has this additional protective layer around the outside. And many of the big problems we're facing now are caused by gram-negative bacteria. Let me explain how penicillin acts. So, I've told you that peptidoglycan is made enzymatically, and these enzymes, they cross-link, so they join two chains of peptidoglycan together so that you have, it's like making a ladder. And this ultimately forms an envelope around the bacterial cell. And so this shows you the chemical structures of peptidoglycan. There's an enzyme here which is involved and which is attached to one of the chains, and then it attaches that chain to the parallel one. And this is how you get the process of a chain extension and the synthesis of peptidoglycan. Now, the reason beta-lactam antibiotics work is that because a key component of peptidoglycan is this simple amino acid repeat, della, della, dealanine, dealanine. And here you have the chemical structure of della, della, and you'll see that, for instance, there are three keto groups here. There are three oxygen atoms there, and if you compare it to the structure of penicillin, you see that penicillin has the same three oxygens, and that there are other similarities in its structure, so these two amines, for instance, to that of della. And so if we put the two molecules on top of each other, you see that penicillin and della are perfectly superimposable. So the enzyme which produces peptidoglycan mistakes penicillin for its substrate. It binds penicillin and then becomes inactivated, and peptidoglycan synthesis can no longer occur, and the bacteria lies and die. So that's what we want to do, kill bacteria. But resistance mechanisms have arisen, and one of the most common resistance mechanisms is due to degradation or destruction of the antibiotic. And a major mechanism which impacts the beta-lactam, so this family which contains penicillins, cephalosporins, and carbapenems, is the production of a beta-lactamase enzyme. So here we have a carbapenem. This is meropenem. It's an antibiotic administered by injection as a last resort when all other antibiotics have failed. Meropenem can be inactivated by bacteria that produce this beta-lactamase. And this shows you the three-dimensional structure of the beta-lactamase. And here you can see meropenem in purple bound to the active site of the enzyme. If we zoom into the active site, you can see the different amino acid residues that contact meropenem, and this serine residue here is responsible for its cleavage. And so the beta-lactamase cleaves the bond here, and you converts it to an inactive form, and the bacteria can now carry on growing. Now, resistance mechanisms like beta-lactamase production are very common, and they're present in what we call the escape pathogens. So this is a group of 6 major bacteria which are commonly responsible for most of the infections that occur in hospitals or in the community. And these are the ones that are causing us most concern. So let us look now at how and where resistance to antibiotics occurs. So I've already told you penicillin is nearly 100 years old. So it's been used for almost a century. So it's not surprising, really, that resistance has arisen. It's been extensively used, and in general, antibiotics are overused. They're sometimes used inappropriately. So many people, when they have a cold, they go to their doctor and they ask to be treated with an antibiotic. But if the cold is caused by a virus, a rhinovirus, or a coronavirus, as is often the case, the antibiotic will do nothing. Beta-lactams only act on bacteria. So if you use an antibiotic inappropriately in a condition like that, this can generate resistance in the bacteria present in the body of the patient. Another reason is due to the use of poor quality drugs, drugs which don't contain enough active ingredient. And this often occurs in the developing world, for instance, where people traffic the drugs, try and make more copies from the same amount of active ingredient, or even sell counterfeit drugs. So this can lead to resistance occurring. The main places where antimicrobial resistance occur are in settings where antibiotics are used intensively. And the first of these is in hospitals or clinics where very ill people are present. And the second one is in agriculture. And I'd now like to tell you a few things about the use of antibiotics in agriculture. This is a really serious problem. Here you see a human being, here you see a chicken. So currently, there are 4 times more antibiotics used in agriculture than there are in human medicine. Often, the very same antibiotics that are used to treat human infections are used in chickens or pigs. And this is absolutely irresponsible, in my opinion. The amount of antibiotics that's going to be used in the agricultural sector will increase. The human population is increasing. There will be greater demand for meat and dairy products and so on. And so the problem is going to get worse. Antibiotics are not used in the agricultural sector because the animals are sick. They're used to make them grow faster. So they're used as a growth promoter. And I think this is something which has been banned in the European Union, and antibiotics are now used in Europe only in the agricultural sector when animals have real infections. But in the rest of the world, in the United States, for instance, it's economics that drives agriculture, and so antibiotics are used because they can produce more meat more rapidly. This is shocking, in my opinion. I'd like to show you now how you can avoid using antibiotics in agriculture, and this is an example taken from the Norwegian fish farming industry, the salmon industry. And here you have a graph from the Norwegian Veterinary Authority's annual report, which shows you on this axis the amount of antibiotics used in tons, and over here we have the timeline, the years, and here the yield, or the amount of fish produced. And you can see that fish production has, in Norway, has steadily increased, and antibiotic consumption has decreased. This is really good news. So what happened? In the early 80s, scientists understood that the fish that were getting infected in the fish farms could be prevented, this infection could be prevented by vaccination. So they introduced a first-generation vaccine, and then they boosted this vaccine by using adjuvants, things which make vaccines work better and at lower concentrations. And you can see that since that combination was used, hardly any antibiotics have been consumed in the agricultural sector in Norway. They now have a much better vaccine which protects against a whole range of pathogens, and you can see that this has contributed to the success of the Norwegian salmon farming industry, and the very small amounts of antibiotics that are consumed now are in cases of infection rather than just to prevent infection, which was the case there. So this shows you that science can contribute to eliminating the use of antibiotics in agriculture in a rational way, in this case by the introduction of a good vaccine. Let us now turn to the global AMR burden. And this is an article which was published shortly before the UN Assembly in The Lancet, which presents the global burden of bacterial antimicrobial resistance in the time frame 1990 to 2021. And they also forecast what is going to happen in 2050. And as was expected for a topic of this major importance, this article was taken up by all the world's best newspapers, including the Corriere della Sera. And I don't know if Luigi wrote this article, but I was very pleased to see the coverage. I'm now going to talk you through what this article actually says, right? The global AMR burden. So we have resistance to all classes of antibiotic in all countries, but the problem is much worse in the low and middle income countries. We are fortunate that we live in Europe. This article predicts that 40 million lives will be lost by 2050 unless to antimicrobial resistance unless we take action. Here they give you the number of deaths in 2021, directly attributable to AMR, 1.14 million, indirectly 4.71. So I should explain what the difference between direct and indirect. So for instance, Luigi's uncle who died from a microbial infection would have been in the direct group because it was directly responsible, the bacterium was responsible for the death. In the indirect, this means it's usually a co-infection. For instance, someone with cancer who's infected with an antibiotic-resistant bacterium, but the cause of death is cancer and not the bacterial infection. So it's an association. By 2050, We've been losing nearly 2 million lives a year to AMR, and the indirect, so will be more than 8. The authors of the article say that better hygiene, so cleaner water, hand washing, and so on, these can prevent infections. Improved healthcare, of course, can improve things. Vaccination is an extremely good way of preventing infection with AMR bacteria. The authors also show that a new antibiotic for gram-negative infections could save 92 million lives by 2050. And that's an impressive figure, and I think it justifies significant investment. And let us now look at the demography of the global AMR burden. And this is from the same article. There are 2 colors here. Green is the year 1990, so these are all of the deaths that were reported in 1990. And blue is 2021, the last year for which a comprehensive data set is available. And what you have here in this column is the age range. So we go from, a few months old up to more than 95 years old. On the left-hand side, we have deaths associated with AMR, and on the right-hand side, deaths that are directly attributable to AMR. And what you can see is that in 1990, the main burden of mortality was down here in the under 5-year-old group. In 2021, this has been, the curve has now shifted, and the peak of mortality is in the elderly. The world is aging, there are more and more elderly people, so we can expect this to continue rising. Why did the under 5s suddenly become protected against AMR? Well, in part it was due to better hygiene, but another major reason is because of the introduction of the pneumococcal vaccine, a vaccine which protects against pneumonia, which is a main killer of young children. And so this has shifted the curve, and I think that was a very important development. What this figure also tells us is that age matters. The elderly population is now more at risk than from an AMR infection than they were 30 years ago. If we look at the global burden country by country, you can see it plotted out here. If the countries are in blue, that means things are not too bad. If they're in yellow, orange, or red, that means things were pretty concerning. And this is the year 2021, and you're looking at the number of deaths per 100,000. So you can see that Central Africa was a bad place to be in terms of deaths from AMR. The Russian Federation and associated countries were not too good, as was the Indian subcontinent. And if we now look to see what the authors predict for 2050, the situation is really, really alarming. South America now is predicted to have serious problems from antimicrobial resistance, with greatly increased mortality by 2050 if nothing changes. China and the Indian subcontinent, the Russian Federation and Eastern Europe are also predicted to have a much higher burden of mortality if nothing changes. So we have to act. As scientists, as responsible citizens, we have to do something. I'd like to now read out one of the concluding remarks from this Lancet paper. The authors say, given the high variability of AMR burden by location, so geography, and age, it is important that interventions combine infection prevention, vaccination, minimization of inappropriate antibiotic use in farming and in humans, and research into new antibiotics to mitigate the number of AMR deaths that are forecasted for 2050. I have put this part here in bold, research into new antibiotics. And I'm now going to transition and tell you what is in the antibiotics pipeline. Here I'm showing you two figures. This one, the title says, the antibiotic market has failed, and this was from a study done by the Wellcome Trust, a British NGO, and this is from an economics report. I will start by the Wellcome Trust study. Here you have the timeline, and I can't read the writing. It's from, I think, from the 80s to about the mid-2010s. The number of new antibiotics being introduced into the clinic is steadily declining, and in the last year it was about 2 or 3. More importantly, the number of pharmaceutical companies, so the big pharmaceutical companies, the ones with giant budgets, has reduced from 18 in 1980 to only 5 nowadays. So there are only 5 major pharmaceutical companies still doing research on antibiotics. So why is that? Well, the answer comes from this analysis, which presents the profits made from the top 200 selling medicines. And it's from the year 2022, and as we all remember, 2022 was the tail end of the COVID pandemic. So the best-selling medicine in that year was the RNA vaccine against SARS coronavirus 2, which generated billions of profit. The next best-selling was Keytruda, which is a monoclonal antibody used as a checkpoint inhibitor in cancer. This is a very effective treatment. And here we have another one. In the top 200 best-selling medicines, there are no antibiotics. There's only one intervention which is active against bacteria, and that is the pneumococcal vaccine that I suspect was responsible for saving all those lives in the under 5 age group. So this is a pretty scary scenario. So big pharma have almost gone from this area, and the biotechnology sector lacks funding. As you know, pharma do little research and development these days, and especially around antibiotics. They rely on acquisitions to fill their pipeline. So they buy up biotech companies, for instance, to buy in their products at an early stage. So this means that all of the de-risking for new medicines, new antibiotics, is done by academia and biotechs. So when a company purchases a biotech, they're fairly sure that the product will work. However, the biotechs which have been working in the antibiotic space are encountering severe difficulty in gaining funding. Venture capital doesn't want to invest in antibiotics because the profit margins are too low. I think it was in 2020, these two biotech companies, Acoagen and Melinta, filed for bankruptcy after taking their product through clinical trials onto the market because they couldn't generate enough revenue to sustain the company. And that is, a tragedy. So one of the big problems that we're facing is economics. It's costly to develop a new medicine, and there are often failures in clinical trials. 1 in 10 new drugs which enters clinical trials will actually make it to the market. So there's a high rate of attrition. The antibiotics which are currently available are very, very inexpensive. And this means that if you introduce a new one, then you're at a competitive disadvantage because the health authorities will always go for what costs less. In addition, new medicines are generally used sparingly to protect the antibiotic, and they're more commonly used as a last resort medicine. So this means that the volume of sales will be rather small. In addition, most bacterial infections, the drug is only used, say, for 5 or most 7 days. Compare this to cardiovascular disease, where people take drugs every day, or to cancer, or to diabetes. And these are the areas of disease where the big profits are being made. Antibiotics are neglected, but their value to society is immense. So something has to change. We can't go on like this, or we will be in a world without antibiotics. So a number of different initiatives have been taken. These have been referred to as the push and pull initiatives. So by pushing, we mean making funds available to academia, to startup companies to do work on this space, in this space, and to do the early clinical, the preclinical and early clinical development of new antibiotics. And so there are quite a few non-governmental organizations such as CARB-X, GARD-P in Geneva, the TB Drug Alliance, and the AMR Accelerator in the European Union, which are examples of push mechanisms receiving funds from the public sector, some funds from the private sector, and often a lot of support from philanthropy. So these are public-private partnerships. They involve academia, small, medium enterprises, and big companies. When you get to the late stage of clinical development, so this would be phase 3 clinical trials, the expenses rocket. So it costs generally about 100 times more to do a phase 3 trial than to do the phase 1, the first part of the process. And this is where funding becomes very scarce. So we need another mechanism to try and compensate for that. And this has been referred to as the pull initiative, and this generally takes place at the level of the government. So in 2016, this report was published by the UK government, and it's generally referred to as the O'Neill report, because Lord O'Neill was the economist who was behind the group that produced this report. And they analyzed antibiotic production as if it was a source of wealth generation. And they conclude that the return on investment for antibiotics is fantastic, but it's very difficult to get people to invest. So they encouraged governments to award financial incentives to bring drugs to market, what they call market entry rewards. So this could be, for instance, a lump sum payment. So if a company brings a new antibiotic into the market, then they would get, shall we say, $10 billion as a result for their investment. It usually costs over $1 billion to get a drug there. So O'Neill has proposed what he calls the Netflix model, where the drugs are used in a rational manner, and I'll tell you more about this towards the end. As with Netflix, you pay a subscription, and you can watch as many shows as you want, or none at all. And so this, I think, is an interesting model. Another thing which has been proposed is to extend the patent life for antibiotics. Patents normally last for 20 years, but perhaps in the case of antibiotics, this should be extended. So I expect you're all feeling a bit gloomy now, because it's all bad news, right? So I would like to tell you a little bit of a success story, or actually there are 2 success stories here. One of them is around tuberculosis. So here you have an X-ray showing the lung of a TB patient with these cloudy regions where the infection is. And over here you have George W. Bush. Now, I'm not a big fan of the Republicans, and this has nothing to do with the upcoming US elections, but I would like to give credit to George W. Bush because he did something which was remarkable. He launched something which is referred to as PEPFAR, the President's Emergency Plan for AIDS Relief. Why did he do that? Well, he was visiting an African country, and he learned that most of the people in those countries did not have access to antiretrovirals to protect themselves from and cure themselves from HIV infection. So he told the head of NIH, launch an initiative to change this. And this resulted in a huge influx of money into the HIV area and a whole new generation of antiretrovirals. As a collateral, it also had an impact on the field of tuberculosis, because tuberculosis and HIV go together in many countries. In sub-Saharan Africa, for instance, patients will be infected with both pathogens. Let me talk you through what's been done in TB in the last 30 years. In 1994, there were 15 million new cases of TB and 3 million deaths a year. In 2024, we have 10.6 million cases and 1.3 million deaths a year. And I remind you that the world's population has increased quite a bit in those 30 years. So we're not doing much. The impact on terms of new cases is modest, but in terms of preventing deaths, we're doing a lot better. And this is because there's now better rollout of drugs to treat tuberculosis, thanks to initiatives such as PEPFAR, to the Global Fund, the UN, and so on. So we have better drug supply, better perspective. And there's also been increased investment in research. So we now have a whole new generation of improved diagnostics and drugs which are appearing. And this research has been funded by the European Union, by the National Institutes of Health, Bill and Melinda Gates Foundation, Wellcome Trust, and many others. I'm going to give you an example of a push initiative around tuberculosis. And this is what's called the European Regimen Accelerator for Tuberculosis, which is a public-private partnership funded by the European Commission as part of its Innovative Medicines Initiative. And in this ERA40B consortium, there are 31 partners, 22 from academia, 3 small-medium enterprises, and 6 FPR partners. So this is the European Federation of Pharmaceutical Industries. So we have a total budget of 207 million for this time frame, and there's 90 million of new money in there. And Italy is well represented in the ERA4TB consortium. You have the University of Pavia, Padua, and the Consiglio Nazionale delle Ricerche, which are also all major players in this ERA40B initiative. As I've said, it's funded by the European Commission, and Europe should be applauded for taking these initiatives. In the field of tuberculosis, there's now a new treatment which is available for the multi-drug resistant form. So this is, if you like, a contributor to AMR, multi-drug resistant tuberculosis. This treatment is called BPAL, after the 3 drugs that are involved. The current treatment for this previously deadly disease consists of taking these 5 tablets once a day for 6 months. The previous treatment involved taking in excess of 14,000 pills, and there were also injections involved for more than 18 months. So this is a radical improvement in the treatment of drug-resistant tuberculosis, and the ERA40B consortium that I just mentioned is actively working on improving this and trying to reduce the duration of treatment even further. As a result of this new treatment, 800,000 MDR-TB patients have been treated and cured. And by curing those patients, you've prevented 6 million new infections arising. So, science can make change. Science is transformative. But tuberculosis is much simpler than the general problem of antimicrobial resistance because it results from infection with a single pathogen, Mycobacterium tuberculosis. AMR is a blanket term. There are probably 10 different bacteria in there which are responsible, which contribute to different infections. So really, we need to tackle them one by one, because I think the chances of finding a new antibiotic that kills all of them are very, very, very slim. And so this brings me now to a new UK initiative, a new push mechanism that I'm involved in. This is what's called the INEOS Oxford Institute, and it's part of the University of Oxford. And Oxford is a special place in the field and history of antibiotic development, because it was at Oxford University that penicillin was first isolated, purified, and the production scaled up for medical use. And so it's fitting that there should be this institute set up in Oxford. It's been funded with a gift of £100 million from INEOS. INEOS is a private company working in the petrochemical sector. And the main owner of INEOS is Sir Jim Ratcliffe, who the tifosi in the audience will know is now the main owner of Manchester United Football Club. And so we're hoping that IOI, the INEOS Oxford Institute, will actually be more successful than Manchester United have been in recent times. So the aims of the IOI are to become a biomedical institute with world-leading expertise around AMR and development of new antibacterials, and for it to become the sort of go-to place in the UK for AMR research. One of the things which we've done is established a network of AMR researchers in Oxford, which comprises over 200 different scientists and clinicians. And these are the areas where we're working, so antimicrobial drug development, surveillance and epidemiology, pathogenesis, so disease cause, genetics and evolution. We're active in this healthcare intervention and antimicrobial space. We're working on new diagnostics, and we're also working on the social dimensions of AMR, doing outreach activities such as this, explaining the importance of tackling this growing problem of antimicrobial resistance. I'm now nearing the end, and I'm going to tell you how you can help reduce AMR. So my first comment would be by using antibiotics sensibly. So if possible, get your physician to do a diagnostic test to make sure that he's going to prescribe an antibiotic for a bacterial infection and not just for another rhinitis. Another way of doing this would be to boycott food which is produced using antibiotics. So if you look these days, for instance, most fish products will say produced without antibiotics on them. So I think that is a good initiative. Lombardy is one of the wealthiest parts of Europe. And I'm sure there are people in this region who have some spare cash and who invest in private equity, in the stock market, and so on. And so I think if you want to contribute to fighting AMR, I would urge you not to invest in companies that use antibiotics in food production. So probably the biggest way we can make a difference is through politics, by lobbying the government and by lobbying health authorities to First of all, support research and development in the AMR area, so encourage more push mechanisms, and also to organize, to get together at a supranational level in order to have better pull mechanisms. And so, for instance, I think it would be interesting if the European Union explored this subscription model, the Netflix model, to see if that would be a better way of supporting the development of new antimicrobials and antibiotics. So in this mechanism, pharma companies would be paid upfront for the product based on the value to the health system rather than how much the product is used. So give this some thought. I'm sure many of you have been active in the fight against global warming. This global warming is also a driver for antimicrobial resistance. These two are interconnected. So please reflect on how you can contribute. My last slide presents some potential solutions to antimicrobial resistance. So I hope I've shown you with the example from the tuberculosis field that science can make a difference, that antimicrobial resistance is a scientifically tractable problem. Society also is a major player in this. By changing our behavior, by acting more responsibly, we can also contribute to reducing the burden of antimicrobial resistance. But major change, transformative change, will require economics, a significant financial investment, much more investment than has been done in the past 20 years. And I think this can only come around through politics, through a political steer. Remember President Bush and his PEPFAR initiative. This has saved millions of lives from HIV/AIDS and from tuberculosis. We need a strong political leader to take up the baton and say, AMR is a major problem for the world, and my colleagues are prepared to unite a group of like-minded political leaders to try and make a difference. So thank you very much for listening, and my venture into Italian. Grazie mille.
Allora, io ringrazio.
So I'd like to thank also on your behalf, I'm sure, but also personally, Professor Cole for this magnificent presentation. I had 12 questions. I have no more questions to ask. He's answered all of them. He was so exhaustive. Very little remains to be asked. Just a remark. We spoke a lot about the economic return, the return on investment when you invest in antibiotics. In a society like ours, this is crucial. And it also has an impact on the intellectual investment. I read a report in which it was said that currently, with 46,000 researchers committed in the development of drugs and research on cancer, there are only 3,000 currently dealing with AMR. So 46,000 for cancer, 3,000 for AMR. I wanted a comment by you on this.
Yeah. Okay, well, thank you. That's a very, very important, it's a critical question. So the pharma sector has disengaged from making antibiotics because it is not as profitable for them as it is to make a cancer drug. So Luigi gave you the statistics, the relative workforces. Nowadays, pharma companies put their best scientists on the projects which will generate the biggest profits. So it's all down to economics. Now think about where the investment in pharma companies comes from. It comes from us. Our pension funds are major investors in the pharmaceutical sector because traditionally the pharmaceutical sector has generated big returns on investment. So we, as citizens, are in a way harming ourselves. We need to convince the investors to invest in AMR research and the development of new antibacterials. The value of antibacterials to society is just as great as that of developing a cancer drug. Or a lot of cancer patients are immune suppressed. They get infected with a bacterium. If the bacterium is susceptible to the antibiotic, they're cured. If it's not susceptible, then they may die. If they die, well, then you could say the investment in the cancer therapy was wasted. Or
sto ancora per una domanda.
One more question, and then I'll leave room to you. As to this issue of investments, Professor Cole rightly emphasized that you should not be investing in companies using antibiotics in farming or animal husbandry, or using antibiotics for animal husbandry. This aspect is very important. Professor Cole underlined, I'd like to emphasize this again, we can do our bit in the field of AMR, as we can do something for climate change. Any small gesture on our side is important. It is important to use antibiotics in an appropriate manner. We shouldn't be insisting with our GP to get antibiotics when the GP doesn't want to. And it is also important to make the right economic choices so that we can improve such a problem.
There's nothing that you've just said with which I disagree.
Yes, I would like to know if you agree with me.
Yeah, completely.
Yeah. Okay. Ci sono domande?
Are there questions from the floor or questions on the chat that the volunteers can read? Please wait for the microphone if you want to ask a question. Thank you. Thank you so much for this lecture that opened my mind, that allowed me to improve my knowledge in this field. I had just a vague idea about AMR. Given that we want to be protected against diseases, what are the microbes we should keep away from? Because these microbes or bacteria are resistant to antibiotics, which are the diseases. So how could we protect ourselves?
Okay, well, thank you for your kind remarks, first of all, and also thank you for this important question. So for reasons of time, I didn't go into all the different pathogens and different bacteria which are responsible for nasty diseases and associated with AMR, but they fall under this group known as escape. So the E stands for E. coli, the S is for Staphylococcus aureus, the K is for Klebsiella pneumoniae, the A is for Acinetobacter, the P is for Pseudomonas, and I think the E is for Enterococcus. Let me just talk about the S, so Staphylococcus aureus. So this is Staphylococcus aureus is a very common bacterium. Many of us carry it on our skin, and if it can cause wound infections and sepsis. Previously, Staphylococcus aureus was treated with a beta-lactam antibiotic called methicillin. Nowadays, Staphylococcus aureus is resistant to methicillin, or pretty much in all cases. And we find it very difficult to treat those infections. I think if I were designing a new research program, I think it would be extremely important to develop a vaccine against Staphylococcus aureus. It's a common cause of nosocomial infection. People who go into hospital for a hip transplant or minor surgery often come home with a staph infection. And in that Lancet report that the Corriere della Sera highlighted, they say that there's been a big increase in the number of infections and mortality due to Staphylococcus aureus. So I think that's an area where we need to do something. But all of the Acinetobacter, for instance, that was never a problem in medicine until antibiotics were overused, and then it became resistant and started causing hospital infections. It's an ecological thing as well as a medical problem.
Altre domande?
Are there further questions?
Buongiorno.
Good afternoon. My question is connected to the fact that very likely in our bodies we have the best antiviral antibiotic in the world, that is the microbiota. If it is healthy, if you read could it contribute to reducing the use of antibiotics or drugs, generally speaking?
Yeah. Thank you for your question. That is a very pertinent and also very, should we say, timely topic, the exploration of the microbiota. I mean, the microorganisms which live in us and a part of us do protect us. So that is very clearly demonstrated. And probably we don't understand how yet, but that will come by tuning the microbiota. You might be able, for instance, there's a very close connection between the microbiota and the immune system. The microbiota primes the immune system protects us against infection, against other diseases. So maybe you could identify a component of the microbiota which could boost this, and that would then give you added protection against infection with an antimicrobial resistant pathogen. I think it's certainly worth exploring. It's less simple than some of the other approaches, but it's definitely worth examining. Why do some people never get infections, for instance? What is the reason for that? Well, in part, it's due to their genes, their immunogenetics, and in part, it could be due to the microbiota that they harbor, which confers some, protection by an unknown mechanism. Yeah, at the back.
Miss.
Hi, thank you so much, very interesting. I wanted you to comment further on the NGOs that you were mentioning among the PUSH initiatives.
Yeah.
How do they work? Do they do research, or they just fund research in other institutes or around the world?
Yeah, well, so the NGOs that I listed, I would say are operational. They're involved in translational research. So let me just give you an example. So GARD-P, I forget what it stands for. This is a spin-off from the Drugs for Neglected Diseases initiative, which worked mainly on parasitic disease. GARD-P is focusing on AMR, and they try to develop new drugs in a simpler, more cost-effective way than the pharmaceutical industry does. I think they have an annual budget of about 130 million euros. Some of this comes from government grants, some of it comes from philanthropy, some of it comes as in-kind from the pharmaceutical industry. So what GARD-P is doing is like the front end of the development process. They will do the late stage research. They will take a lead molecule into clinical development, do early stage clinical trials, and then the financial hurdle gets much higher, and so with the budget that they have, they would probably struggle to do many phase 3 trials. But so it's a mixture, I would say, of good science and good citizenship.
Altre domande? Quante? Allora.
Are there other questions? How many? I do not know who raised the hand first. I'd like to ask the following. The very first antibiotics was discovered randomly by Fleming, and serendipity often is supporting talents. What could be the levers to promote scientific curiosity even well beyond the issue of profits or revenues?
Well, no, thank you for the question. I mean, serendipity is certainly important, but I mean, as Louis Pasteur said, chance favors the prepared mind. So if you've been well trained and you're well educated, then you're much more likely to spot these opportunities, this serendipity, than if you haven't. So the underlying factor, the most important factor of all, is higher education.
Qua davanti ce ne sono diversi. Poi anche là.
Hi, good morning. I wanted to
Buongiorno, le volevo chiedere se lei pensa
and if they can create a vaccine against obesity.
Well, antibiotics could contribute to controlling obesity, because often obesity results from a change in the microbiota, and that there are bacteria which help the body make more fat. But I mean, the current anti-obesity treatments which have come along, things like Wegovy and the anti-GLP-1 drugs, these seem to be incredibly effective, and they also have, I think, far-reaching consequences and seem to, positively impact cardiovascular health and a few, maybe even some neurological conditions. So I doubt whether it would be an interesting area for further use of antibiotics. And again, there would be an economic argument. You have a really effective drug that's doing this. Admittedly, it's costly at the moment, but you would have to come up with something which was just as good and probably less expensive.
Salve. Allora,
Well, first of all, thank you very much for your conference. I have a question for the intensive use in agriculture of antibiotics. Why is it that antibiotics allow animals to become bigger and fatter? How does it work? What is the association between having a bigger animal and the use of antibiotics? I didn't get this.
Well, by adding antibiotics to the food or the drinking water, it can prevent some minor infections, and it can also take out some of the bacteria present in the animal's body, which slow down its growth. But when you look at the benefits from using antibiotics in terms of the growth promotion, when I last read these articles, it was a difference of something like 15%, which in my mind wasn't that, you know, I felt that 15% is better to not use the antibiotic. But if you're doing high throughput, intensive agriculture, then this would make a difference. And I mean, I think personally, I feel agricultural practice needs to change and that we need to go towards a more sustainable form of agriculture. But sadly, in some parts of the world, in the low and middle income countries where they don't have enough high protein food sources, this is seen as a good way forward. And so, it's not, I don't think, a coincidence that the main problems of antimicrobial resistance are in those countries, because this is often where the use of antibiotics is at its most, shall we say, uncontrolled.
Altre domande? Qua ce n'è una. Qua davanti.
We have a question here. Thank you. Very, very interesting report. But I wanted to ask you this. I don't know if it's the right question to ask. The relationship between GMOs and resistance, antibiotic resistance. Maybe the use of GMOs could be useful to study, to research antibiotic resistance. What do you think? Is there a connection?
No, that's a complex question, so I have to break it down into its component parts. So GMOs, I mean, I think if they're done properly, are of great benefit to society and to agriculture and medicine. By improving, for instance, the protein content of a food, you could boost the immune system of people who eat that food, because the immune system is very demanding in terms of energy and protein. And so if you boosted the immune system of an individual through diet, then that would protect them against infection. So it's an indirect mechanism. There's a direct link between malnutrition and infection.
Altre domande qua? La una in fondo.
I see a question back there.
Allora, innanzitutto ci tenevo.
First of all, I wanted to thank you very, very much for your presentation. My question is the following. If antibiotics are introduced in animals and in agriculture, couldn't they maybe alter, or couldn't they maybe be subject to alterations and become something negative for men?
Absolutely, yeah. The use of antibiotics in agriculture or the environment is bad news for human beings, because antibiotics are extremely powerful selective agents, and they can select for resistance in environmental bacteria, for instance. And these environmental bacteria could then become a source of infection, or more likely, by harboring the resistance genes, they may then, for instance, swap those genes with the ones that transfer them into those of bacteria which normally are inoffensive in a human body. And so if there is an amazing selective pressure from antibiotic use. If you look in water systems, for instance, the Lake Geneva that I used to follow quite often was often very polluted by antibiotics and by contraceptives, which are stable molecules that get into the water system and end up in the environment. And so they carry on. I mean, antibiotics come from nature. They're produced originally by bacteria that live in the soil. So, the circle is complete. But we may, for instance, many of the antibiotics which are produced by pharmaceutical companies are often better than those produced by microorganisms because they've been optimized to be effective.
Altre domande? Non ne vedo.
I don't see other questions, so I have two final questions for the professor before letting you go. The first is this. In your presentation, you underlined that vaccination is one of the ways to contrast AMR. Why should we support vaccine campaigns, even against the viruses, for instance, the flu vaccine, COVID vaccines? How can this positively contribute in reducing antibiotic resistance?
Well, that's an excellent question, and I think we've seen quite a lot of good examples of how the use of vaccination prevents infections from other microorganisms in humans, and how in turn this impacts on the use of antibiotics. And I will give you an example. It's one which I've cited repeatedly during my presentation, the pneumococcal vaccine. Since the introduction of the polyvalent pneumococcal vaccine for immunizing children, the number of prescriptions of antibiotics in that age group has gone down quite significantly. And by protecting those children, you are also removing a source of infection. If, like me, you're a grandfather and you spend some time with your grandchildren who have pneumonia, and they can infect you. So by protecting them, you're protecting yourself.
Ok, direi che è molto chiaro. Ultimissima domanda, una curiosità.
Very last question out of my own curiosity. I read extremely interesting papers on how generative AI can contribute to the so-called protein folding, to understanding how proteins fold, how they configure in space. I'm asking, given such results, to what an extent generative AI can help us designing new antibiotic molecules, thinking of the beta-lactamase inhibitors, extremely important, that attaching to existing antibiotics can sort of rejuvenate them.
Yeah, thank you, Luigi. So AI is going to save the world. It's cited everywhere these days. But I mean, but if you look at what it can do, and what works well at present is through machine learning, you can handle large data sets, much more information than was previously possible. And this has had a number of consequences. So, for instance, you were alluding to the introduction of a new software which was called AlphaFold, which is powered by AI and machine learning. And AlphaFold can predict the three-dimensional structures of proteins. And proteins are usually the targets for drugs and antibiotics. And thanks to better tools for predicting the structures, we can then design inhibitors which interact with that particular target in a more effective way and a more efficient way. So I think AI has tremendous promise and is finding use in drug discovery and drug development. So we need all the best tools we can employ, and that is one of them.
Thank you. Bene, direi che possiamo chiudere qui anche.
I would say we can close here because no more time is available. I would really like to thank Professor Cole for his lecture. It was exhaustive, extremely clear, crystal clear, very interesting, and interpreters would like to thank you because this was very clear. Thank you very much.
Grazie a voi.
Thank you to you all for your active participation. See you soon. Bye.